Yeah, so I'm a scientist who studies water in its frozen form, as in ice, and I'm now at the Canadian Ice Service, so that's fitting. And I've had a love for ice for many years. In fact, in high school, in grade 10, we did this physics experiment where we tried to determine how much energy it takes to melt ice. And my lab partner at the time was a bit jaded, not too cool for school type, and he said, "Oh, why do we have to do this? Everybody knows that ice melts at 0 degrees." And nowadays, he totally missed the point of the whole experiment, and he's now a lawyer in New York City making figures, and I'm sitting here thinking about melting ice to this day. So ice is not just fascinating to me, it's actually terribly important. The Arctic, it's far away from us now. It seems removed in our minds right now, but it is critically important for our planet's climate system. And ice and snow, likewise, are critically important for our planet's water cycle. So, and of course, the Arctic is changing. We've got what goes around comes around. So what happens to our water here is certainly linked to the water in the Arctic, and what happens in the Arctic will eventually reverberate throughout the planet. So we have a lot of changes ongoing in the Arctic, and today I want to sort of give a broad brush view of some of the major changes. I don't have time to go into any detail, but I will go into some detail about halfway through my talk on my own research, which is on ice shelves at the northern end of Canada. So this is a little climate background. We have here all of these little lines are how scientists have tried to reconstruct the climate. You can see here the temperature, it goes up and down over time. But recently, here's where we've measured temperatures that are going way up now, heading off the chart here. So what we're seeing is that vis-a-vis the last 1,000 years or 1,200 years or so, we're really exceeding the limits of natural variability in our climate system, and we're headed towards warmer territory. And I'm sure you're all aware of climate modeling and the efforts that are going on to understand how our impact on the climate, our greenhouse gases, are going to change climate in the future. And you see here a lot of different models. Like here's today, year 2000 roughly here, and this is what we've had in terms of climate warming. And we're in for a rude surprise over the next century. Even if we stopped all greenhouse gas emissions and held them steady at about year 2000 concentrations, we would still be warming. So we're heading up into this territory, which is about 2, 3, 4 degrees, depending on which models and which scenarios you're talking about. And that's a global average. And this morning, Chris was talking about averages and how difficult they are to sort of comprehend. And this is a planet-wide average, and I'll show you what that looks like in terms of the Arctic. And I know it's very poor lighting in here, but this map here, it looks sort of like a dartboard with the red colors in the middle and oranges and yellows on the outside. Well, that is a temperature scale of what will be changes in temperature looking down on planet Earth at the North Pole. So this is Canada here. And basically the take-home message of this graph is that what we're predicting for change in the coming 100 years or so will occur most and firstly in the Arctic. So this is what's known as polar amplification of climate warming. So what we realize is that the Arctic is essentially our planet's canary in the coal mine, if you will. And there are several examples here of changes that we would expect to occur in a warming scenario in the Arctic. And indeed, these are occurring right now. We've got permafrost, frozen ground that is underlaying a lot of land in the Arctic, melting and shifting, and then that causes buildings to collapse. It causes forests to fall over. This is what's known as a drunken forest, where the trees are just basically fall over because the ground that they're on melts away, essentially. I mean, the ground doesn't, but there's a lot of ice in it, and if that ice melts, those trees fall down. Greenland, for instance, is the biggest ice mass in the northern hemisphere, second to Antarctica in planet-wide. So it's just a major ice mass, and its melt is accelerating as well. So these are these are different canaries, if you will, and they're all singing the same song at this time. They're all saying it's getting warmer here. The climate is warming in the Arctic. And one of the reasons for that is what's known as the ice albedo feedback in technical terms. And this is basically a vicious circle, if you will. You have here the ice and snow. Basically, you're looking at the north polar region here. You've got Canada and Greenland and this sea ice that goes all over the Arctic Ocean in the middle of the Arctic basin, if you can picture that. And there's the sun, and all of that light is getting bounced away from that ice and snow. What the Arctic does for us is it acts as our air conditioning system. It's like a refrigerator. It keeps us cool because of all of that ice and snow. It's reflecting light, and that means energy and heat away from the planet and keeping us cool. Well, as the ice melts, less and less ice is there to absorb, to send away that solar radiation, and basically what happens is the water underneath absorbs that energy. And even if it doesn't raise the temperature of the water very much, it is adding heat into the planet system instead of bouncing it away. So it's a feedback loop. It's a vicious circle where the more warming you have, the less ice you have, therefore the more warming you have, and on and on and on until there's very little ice left. And that is sort of manifested in some ways. It's obviously there's a lot of complexities in the system, but with Arctic sea ice and what scientists look at as an indicator of these changes is the minimum ice extent. So sea ice is like, it grows and shrinks with the seasons. So even if there's no sea ice here in the summer, in the winter, of course, the sea ice will form. I mean, this is all normal, and it will continue on and on like this until the planet gets exceedingly warm, which is beyond any of the models can predict. But in the summer, the sea ice shrinks back to its minimum extent in around September 14th, which is sort of the end of the summer in the Arctic. And this is then the area that was covered by ice September 14th of 2008, so a year ago almost. And what you can see here is this is the ice remaining that's going to go into becoming a second year or third year or fourth year ice is going to remain in the Arctic. Now this extent used to be much, much more vast, and now we're changing it dramatically. In 2007, for instance, we beat the record by 1.3 million square kilometers. So this is the size of Ontario, or even bigger than Ontario, in fact. Imagine all of that ice and snow that was that used to reflect all of this energy, the sunlight, away from the polar ocean, now gone, and all of that sunlight going into the ocean. And of course, it's no surprise that the 2008, there was no recovery of that million square kilometers. It's almost just about the same as the 2007 record. And we're headed to around the same level. We probably won't beat any records this year, but we're not recovering the ice that we lost in 2007, nor in 2005. And you see, here we have in blue, faint blue line, is this how you can go around the Arctic Ocean here on this day. I think for the first time ever, a completely clear passage right around the polar pack ice in the middle of the ocean. So this is really historical in terms of change. We haven't seen this really ever. And we have models that scientists use to predict these sorts of changes, and all of the models, in fact, show a decrease in ice over time because of the warming and these feedback loops. This vicious circle that I described is captured by the model. But what's interesting is this model here, in fact, this is an average of models, and all the variability in the models here is shown in blue. What we observe is this line here. So we're going down at almost 10% per decade, which is an enormous rate. And then all of a sudden, we're jumping down here. This is the 2007 record that I mentioned, this million square kilometers. This is the Ontario-sized chunk of ice that's missing now. Coming, and it's basically 30 years behind what the models are predicting. So not only are we having these rapid step changes in the ice as it's melting, but it's also surprising everyone in terms of the timing. We don't really understand, well, why is this happening now, and how can we improve the models to capture, because the models are wrong by about 30 years. So we're really in for some surprises, I guess. This is basically what you would consider a tipping point in the system, where all of a sudden you have very little change, very little change, very little change, and all of a sudden a big change. And I'll talk about tipping points when I get to ice shelves. We also may have a point of no return in that it's so difficult with this vicious circle to get ice to form now, because we're warming the ocean, to get this back up, and so it may never recover. Also, I should mention that ice thickness is changing as well. So we have the ice area, the ice extent is reducing, but also the thickness. For instance, in the March here, we have over time the white here is the very thickest ice, and then they're followed by the red, and then the blue is very thin ice. So over time here, as we go forward in time, we're losing this ice, and the thick ice is actually being pushed up over here, which means that the rest of the Arctic has very, very thin ice, and that is obviously easier to melt in the summers. So this is part of the problem as well. And I guess I should mention sea level rise, because that's on people's mind. As Chris mentioned again this morning, that more ice melting means more water available in general. One thing that's interesting is any floating ice, any sea ice that melts, is actually not going to raise the ocean level because it's already floating in the ocean. But glaciers that come from land are, if they melt, will raise the ocean level. And certainly there are big glaciers. Greenland, for instance, has huge outlet glaciers that are accelerating their discharge into the ocean, and of course raising sea level because of this. So here we have temperature rising and sea level rising, and half of the sea level rise is due to glaciers putting more water into the ocean. The other half is from just the heating of the ocean itself. If you heat a cup of water up to make tea, it basically becomes bigger in volume. So you have an expansion of that water, and that will raise the sea level. So half due to the thermodynamics of it, the heating of that water, and half due to just melting of the water. And we have predictions that there will be more sea level rise in the future, obviously, because we have predictions that there will be more warming, but none of them really adequately capture the speed of the glaciers. If the speed of the glaciers flowing into the oceans accelerates, then we don't really understand that process, that glacier dynamics, well enough to be able to predict it, and so it's not included in these models. So I guess the take-home message of that is that we don't really know all of the factors, and we need to catch up really in terms of there could be some ugly surprises in the future in terms of all of our predictions and how they're going to go. So now for the next little bit, I'd like to talk about ice shelves in Canada, and this is really my own research area. So you might wonder, well, where are ice shelves in Canada? Probably some of you didn't even think there were ice shelves in Canada. Well, the answer is they are 5,000 kilometers or so to the north, along the northern coast of Ellesmere Island at the north coast of Canada, essentially. And I'll answer the next question. Well, what are ice shelves? And we think of ice shelves really, when most people think of ice shelves, they think of Antarctica. They think of this massive continent surrounded by, 40% of that icy continent is surrounded by ice shelves. And they're coming from glaciers. They're flowing out over the ocean, and they break off and so on, and they're replaced by snowfall in the interior of the continent. In the Arctic, they're somewhat different. They're not as thick. They're only 10 to 100 meters in thickness. So on average, we'll get about 40 meters thick ice, which is not thick in the context of Antarctica, but when you think of a 10-story building, that's how thick they are. So this is fairly thick ice. Consider this sea ice would be maybe 4 meters, 2 to 4 meters. That's 40 meters. That means the fish is way out of scale. So you see, you've got this ice floating on the ocean, same as in Antarctica, but only sometimes glacially fed. So yes, there are glaciers flowing in, but not necessarily all the time. And they're thousands of years old. So they're between 3,000 and 5,000 years old. So these are very ancient features, certainly on a human time scale. I mean, you think of the Egyptians. They were around when these ice shelves were forming. And now these ice shelves are in decline. And how did they decline? How did they grow? Well, it's basically like sea ice on steroids. If there are no glaciers flowing in, then that sea ice has to grow in place in a colder climate. More snow, more freezing on the bottom, and that ice thickens up over time. In a warmer climate, loss of ice melting on the top or on the bottom, or even the calving of ice islands. And when we think of glaciers calving, like a tidewater glacier, they calve off big icebergs, and icebergs are the size of a building, maybe. Well, ice islands are the size of small cities. So these things are truly massive. Remember, 40 meters thick, 120 meters thick, and the size of a small city. That's why they call them ice islands. So here is, you probably all have heard of Robert Peary, who actually, it was, 100 years ago, this month or last month, he got to the pole, and before he went to the pole, he did some journeys along the northern coast of Ellesmere Island, and as he went along, he reported this strange ice type. He called it the glacial fringe as he was going along, and in fact he cursed this thing because it was full of difficulty for him to travel on. And it went along something like this, and if you can reconstruct that, you come up with almost 9,000 square kilometers of ice shelf. Well, fast forward 100 years to 2005, and there's only this left here, about 1,000, so almost 90% reduction in ice shelves. And this is the north coast of Ellesmere. Some of you have heard of ALERT, a Canadian Forces base up here, and Eureka is over here. And the North Pole would be a couple hundred kilometers to the north here. And one of the main culprits, obviously, is temperature. And you see here this very big warming here in the 1920s and 30s, which is obviously not related to human emissions of greenhouse gas. So it's probably more of a natural cycle. But this certainly is here related to greenhouse gas emissions, where we're warming here. And as we exceed thresholds in temperature, you see break-offs occur. So most of these break-offs probably occurred in here. No one was around to see them. And a few in here. And as we're getting higher in temperature and warmer, we're seeing more break-off events. So this is the breaking off of these ice islands and the destruction of the ice shelves themselves. So let me give you a quick look at one of the ice shelves that broke apart in 2005. This is called the Ailes Ice Shelf, and NASA did an animation of this. So I'll just run this movie, and you'll see zooming in here to the northern coast of Ellesmere Island. I know, it kind of makes me dizzy, but NASA liked it, obviously. And it's going to blink red here so you can see what it is, because ice doesn't show up well against other ice. So that's the ice shelf there in red, and it just peels away from the shore within a time span of several hours, aided, of course, by this open water. Once there's open water in front of the ice shelves, then that allows these pieces of ice to break away from the coastline, where they've been for thousands of years, and float away. In winter of 2008, I had the good fortune of joining Canadian Rangers on a patrol up there, and we did some science with the Rangers, and they reported these massive cracks on another ice shelf along the northern coast of Canada, and this one was called the Wardhunt Ice Shelf. And this is sort of foreshadowing for what occurred in the summer of 2008. So last summer, it was a busy summer for these ice shelves. They changed quite a bit. In fact, they lost 23% of the remaining ice was lost on in the span of a few weeks. So that's 214 square kilometers. Here are the ice shelves in black. I've named them here: the Sursen, the Peterson, the Milne, the Warthunt, and the Markham. And in green here is the boundary of Kootenay National Park. This is Canada's most northerly national park. So obviously a protected area. Well, as we go through it this summer, this is the August of 2007. We thought there was a lot of open water in front of the ice shelves here. In 2008, there was even more open water, and you'll notice a big change in these ice shelves, particularly this one, and this one here. They changed drastically. And I'll just go over that in detail. Here you can see them breaking up with satellite imagery. And on the top here, you see before pictures of what the ice looked like, and afterwards just open water where the ice shelves were. The Markham ice shelf was completely lost, and the Sursen ice shelf over here lost over 60% of its area. And in Antarctica, they like to talk about icebergs as the size of Rhode Island. Well, in the Arctic, we have smaller ice shelves, so we have to have a different comparison. We talk about them in terms of Manhattans. So Markham was just under a Manhattan in size, and if you can picture Manhattan Island. And Sursen ice shelf here lost about 2 Manhattan-sized pieces of ice that broke up into many pieces here in the span of a few weeks. The Warthunt ice shelf here, you can see a loop here of animated of it breaking off in the front here and in the back. It changed a lot in this period, and I told you about the cracks that were discovered in the winter. Here's a before image of the ice shelf and the after image here. Zooming in, I want to show you that on this eastern half, there's riddled with cracks. You can't tell that from this far away, but I'm going to zoom in here with some satellite imagery. We have some great satellite imagery from Taiwan. And you can see here, just randomly selected place, you can see all of these cracks. And now going into black and white, you can zoom in even further and see all of these cracks. So if the ice shelf is riddled with cracks, it's only a matter of time before those pieces are going to come loose and float away. And I just want to mention that this is a one-way change. When you have a crack through an ice shelf, it won't reheal. It may reheal a meter or so on the surface, but basically it's broken through 40 meters of ice, and that is not going to reheal anytime soon. Certainly not in this climate. And if ice shelves break away like they did here in the 1930s, in another climate, you would expect ice to reform and build up, thickening over time until they regain the size and mass of an ice shelf. Well, that's this gray ice here that broke away and is regrowing in place. But in 2005, that ice basically got swept away too. So we're dealing with a sort of a one-way change. This is not going to come back anytime soon. Certainly not in this climate or any projected climate. So when you look out over the surface of these ice shelves, you say, well, this is a glacial landscape. It's just snow and ice, and there's really nothing interesting there. Well, I did some work on the biology of these ice shelves, and I can assure you they're actually alive with organisms, really very rare organisms that you would never expect to find in this kind of a habitat. You can see here this orange color. These are algae that live on the surface of the ice. We call them microbial mats because they lay down over sediments like a carpet. And inside, if you look in with a microscope, you can see all sorts of different organisms that have the tolerance to live in such a cold and hostile environment. So these are quite startling ecosystems. And of course, as the ice shelves disintegrate, break away, and melt elsewhere, these habitats are being lost. In fact, they're on the verge of extinction, these ecosystems. And why would we want to study these? Well, they're perfect analog for why, or perfect to ask the question, well, why are some organisms here in the Arctic on ice, and are they the same as organisms here in Antarctica on another ice shelf. So you can look at both polar regions and compare the biogeography, the biodiversity of these locations on Earth. You can think of how they're adapted to life in their environment. Okay, they're dealing with some very stressful situations. They have these interesting colors, and those turn out to be antioxidants, carotenoids that actually help them deal with really bright light and very low temperatures. So there could be some biotechnological applications, some sunscreening compounds that they use that we could use perhaps. And then another thing that some people like to think about is, are they an analog for times past in Earth when the Earth might have been completely covered with snow and ice during massive glaciations in the past, or even an analog for life on other planets? There are icy planets, icy moons of Jupiter, comets where life can exist, and that's a snow and ice environment as well. So now I'm just going to I want to come back to the predictions in air temperature before I finish up here. And I guess when we look at this target, this bullseye pattern here on the North Pole, and we say that it will warm in the future, we've already know that there are massive changes well outside the limits of natural variability. We've got this irreversible ice shelf loss, changes to ecosystems, and in particular this one I mentioned, but you can pick any other ice ecosystem like polar bears or seals or walrus that depend on ice. But there are more changes to come. So what will happen in the future? And one thing that are a particularly hot topic and political one at that is sovereignty and resource extraction. People think, well, this is great. We're going to be able to go up to the North Pole, and we're going to be able to drive ships right through the Northwest Passage. We're going to be able to mine and extract oil and gas in the Arctic because there's no ice left, or there won't be in a few years. Well, that's a bit of an exaggerated viewpoint. And one particular point I want to make is that there are these ice islands that I mentioned floating around. Now we've got more and more of these ice islands, and this is 7 kilometers from here to here. I mean, these things are massive pieces of ice, and we're not used to dealing with this kind of ice feature in the Arctic. So what we want to do is track where they come from and where they're going along here, for instance, and out here. These are different. This is the Ailes ice shelf that broke apart here in 2005. I showed you that video from NASA. And then it broke into 2 pieces here and then went over this way and that way. And this is the piece of another ice shelf that broke up in the summer of last year. And we're tracking these pieces because they can, again, splinter into many, many different fragments and run into a ship or run into an oil platform or generally wreak havoc where people aren't expecting to see this kind of ice. So there are these sort of surprises, if you will, in changes in the Arctic. Well, you think that it's all going to happen in a very slow and timely manner, but in fact there are step changes and there are things that you don't expect to happen that are occurring. And by the way, if you want to know where these are, you can look them up online. There's links there to their location online. So I guess in summary, I want to mention that there are these profound environmental changes in the Arctic. I went over a few of them. I don't have time, obviously, to go into any detail on many of them, but these changes will affect us all, particularly this concept that the Earth has an air conditioning system, and that is our Arctic snow and ice that's reflecting away solar radiation and keeping us cool. Well, that will eventually go by the wayside, and we will warm as a consequence, planet-wide. So we have this uncertain future. We have these weird step changes that can occur. We have thresholds that we exceed, and all of a sudden there's a tipping point, and we have a major change. But we're getting better at understanding these thresholds. We're getting better at understanding these tipping points. And our research efforts are increasing our understanding scientifically so that our models can be tuned to better understand the changes and better predict the future. And obviously this all boils down to our impact on the planet in general. And I want to end on a positive note, that people are starting to pay attention. People like yourselves here, coming to this festival, learning about the environment, whether it's water here under your feet or water in faraway places. And I really appreciate that, and it certainly gives me hope that we can make changes not only to our own lifestyle, but we can help others make changes as well, and through the political process. So with that, I want to thank you all for your attention and thank the organizers for inviting me. And I have also some websites here if you're interested in other more details.